So this talk, Sydney, can you close the door? Be loud. This is a 2012 paper, and that is almost pre-AlexNet. Why would anyone talk about anything non-deep learning that came out in 2012, right? Well, for those people who kind of cave to authority, I can tell you that ICML in 2022, which is much more recent, right? It's in your lifetime, or at least in many of your lifetime, well, gave it an honorable mention of test of time in the test of time award category. So this paper is interesting, at least for that. Another reason to talk about this paper or to discuss this paper, besides that I finally wanted to read it, is that it talks and summarizes interesting ideas and calls us into looking at problems under a different angle and shows how looking at a problem that was in front of everyone knows all that time under a different angle can bear fruit. Yeah, of course, it's not like a break through everything in one paper. It builds on a lot of other results from other people, including that same group that was published before. So that's why the text that I put in the Slack that is verbatim from the paper is that we're not proving any new theorems, we're not doing any extensive experimentation in this paper, we're just trying to provide an intuition and etc. etc. So, but as I started before starting the recording, I'm giving the same talk all over again. So I will only talk about what I know, not exactly about that paper, which I hope you already read anyways, and you will be able to comment. So they start with a book, briefly citing it, The Direction of Time. So this guy, which I didn't capitalize correctly, Hans Reichenbach, wrote a book, The Direction of Time, that is published posthumously, as you see, that had a huge effect on the study of causality in econometrics, in economics, and in philosophy, etc., etc. He's considered a philosopher, I guess, and that's I found this an interesting case when a philosopher who had actually an impact is mentioned, at least in the paper, rather than just ignored and only technical research is mentioned, because this area of study, the causality research, is inspired, influenced, and advanced by philosophers greatly. So, okay, so the paper starts with The Direction of Time book introduces the principle of common cause. And the principle of common cause states that if two events or variables A and B are correlated, the correlation is just some association, is not necessarily your Pearson favorite correlation metric. So there must be a common cause that explains this correlation. And I was like, when I read this, I took a long pause on searching on the web, etc. It's like, is that true? What does it mean? But we can look at those two structures for now. This is an illustration from the book I don't know if it was this book or before, the idea to connect causality and graph representation. We call it graphical representation, but not in a common sense, in mathematical sense, graphical in the sense of graph. Variables are nodes and arrows are directions of causality and direct causes. So basically, if we have B causes C, then or B arrow C rather, then we mean that within the observed set of those three variables, B is a direct cause of C. And even if there are variables that we did not observe on the way from B to C, they don't have any other influence back to B, say, maybe forward to C, but basically there is like a chain here, only chain. So this one is a direct cause. Information from B flows to C. So relation, data, association measurements, and causality. And again, those who saw my talks that saw the slides multiple times before. Let's get back to our favorite problem. Storks deliver babies, right? And this is also from 2000 paper or a book published in 2000. This is actually true. Highly statistically significant correlation. P is 8,000 that exist before stork populations and human birth rate across Europe. This is true. This is like, I'm not making up. This is not for a joke. So another so make what you want of it, right? But then another study, London taxi drivers. So a survey has pointed out a positive and significant correlation between the number of accidents and wearing codes. So they concluded that codes could hinder movement of driver and be the cause of accidents. And a new law was prepared to prohibit drivers from wearing codes when driving. So those are examples of statistical view. When you read about overweight, like overweightiness, whatever is connected with this, they usually mean, oh, there is a correlation. There is a correlation, like in the first case, and I don't know if I have, let me do something. Sorry, people who are watching the recording. I need notes if I have them. Or at least I need to see where I'm going. Yeah, so turns out the size of rural area and the number of storks, and especially in Europe, is correlated. The more rural area you have, the more habitat space you have for storks, and rural families tend to have more children. So basically.
So Europe's not different than what I was telling you about the US, the suburbs of children, basically.
Any storks in the US?
No, but I saw the first stork I ever saw in Ukraine like a couple of summers ago.
Yeah.
They're very weird birds. They don't move that much once they're
kind of ibises too.
Well, because they only move within big beds.
Yeah.
But then in the US, the same population, but no.
If you look at the cranes, so like in Florida's big sandhill cranes, they're probably pretty big. Like as tall as a person.
Yeah, they also say they find babies in cabbage and etc. There are lots of interesting stories and theories there. Yeah, I'm not sure about this. Is actually, but our theory, this is nature worthy, right? It's statistically significant publication, and I'm not sure about cabbage and other stuff and bamboo and so it's very different stories, but they don't test standard test of p-value testing. Anyways, so in London taxi values, of course, the more accidents, the more rains, the more accidents, and in the rain, driver tends to wear a code. So that's the point of the difference. So in causal view takes interest in interventional questions. Is like with the taxi drivers, I make what you want of the stork story, but with the taxi drivers, is like, let's prohibit them wearing codes. When they come to work, let them, hang the codes on the rack. That's what we want to intervene. We want to reduce the number of accidents. And if you are the consulting company hired by the mayor of London, I don't know, that got a lot of money, and that's your recommendation. Don't wear code. You got your money, but I guess the number of accidents will not decrease. So interventional questions is like, will increasing the number of storks in the country boost its human birth rate? That's the kind of question causal people who are interested in causal learning are interested in. And say, would fewer people smoke if cigarettes were more socially stigmatized? That's also the causal question. So, but the problem is now the question that everyone is asking, I think, and we keep asking it besides all the, like, how many times we speak about is how do we go from data to causal graph? So all we have is data, right? Is the measurement here, whatever, from each point. And how do we use the data to infer a causal graph if all we know, well, if all I know is how to measure correlation, right? So if that's and x is of course 0 mean. So that's the main question, and there are multiple or several at least approaches to the problem. But before we can do that, before we can interpret any graph as causal graph, we need a few assumptions. The paper lists tons of assumptions. The main assumptions that usually come up, and those assumptions have to be satisfied, is the Markov assumption. And the Markov assumption or causal Markov assumption is the same. Is that given a causal graph, each variable is conditionally independent of its non-descendants, given its direct causes. So what it says, if this graph is causal, if you extracted not just many companies are interested right now in this question. The question is called causal effect. And many people in policies, etc., are interested in the question of, well, I know how variables are connected. I know what causes what, but I don't know, even when I know the causal graph, I don't know how much effort should I put here if I want to say have an effect here. I want to change this variable. I don't know, smoking rates in US or something. Should I put a lot of effort here? If I put any effort here, how much will this change? If I put any effort here, how much will this change, etc., etc. So causal Markov assumption just tells you about this graph that, look, for this variable, if you put effort into this two, those variables, the other variables don't matter. So this variable is conditionally, you condition on the parents, is independent of non-descendants if you just condition on the parents. So if you manipulate the parents of this variable, that's all you need. The rest don't matter. That's what causal Markov assumption says. When you know the graph, when the graph is given to you, when you inferred it from somewhere else, you have it. And that's how most people operate dynamic causal learning. Given the graph, run your differential equations, you will compute the values, you will know what happens, and etc., etc. So another assumption is, well, but how do we go back? Can we go back from the data to the graph? For that, we need the faithfulness assumption. And the faithfulness assumption says that conditional independencies, those relate to data. You take the data, test the data, no graph given to you, but it says that the knowledge about the data or results of the test on the data, so the independencies result only from the underlying causal structure. So no fine tuning or coincidental cancellation. So let me give you some examples. So we have, say, 3 variables: exercise, calorie intake, and weight gain. So X, Y, Z, right? So in causal structure, say X causes weight gain and Y causes weight gain, something like that, right? X causes Y, Y causes weight gain. And X and Y are independent. X and Y are independent because, okay, you can exercise as much as you want and eat as much as you want simultaneously, up to a point. Of course, we biological systems sometimes we saturate. So, but faithfulness assumption holds because the observed statistical relations match the causal structure. Exercise and calorie intake are both statistically dependent on weight gain, but exercise and calorie intake are statistically independent of each other. But another example, well, the one I like, the one I have here is kind of funny and more related to my kids. So if you have X as amount of studying Y as amount of playing computer games. Where is Noah, I wonder? C is the exam score. Then the situation is more tricky. So more studying leads to less time for video games, etc., etc. But we may have a coincidental cancellation that, yeah, this is more moralizing story, I guess, but let's use it anyway, that the more you study and then you went to play or TikTok or something and like everything got erased and then you go to score. It doesn't matter how much you study if you watched enough of stuff to just pack in your brain and delete the previous what you learned.
Is that how it works?
My 10-year-old told me, I'm like, the question was, well, you buy link and how do you
Oh no.
store? Yeah, we're just talking about computer game playing.
Shows up. I mean,
Yeah. Computer game playing. So yeah, how do you store two languages in your head? And the theory is up to you. It says, well, imagine you know one language and then your brain is a whole egg kind of thing. You know two languages. The brain splits in two small parts. And then you know 10 languages. It's 10 little, so you know 10 languages crappily, like none of them you know really well.
That's a bad argument. Bad argument.
Yeah, anyways, but the real story is, imagine that you have a computer on which you play game and you don't give anything, whatever, no, it doesn't give about test exam or exam test. So all you care about is playing games. That's why you have a computer generator. You have an energy generator, gasoline powered in your backyard, because you know how Atlanta is. And so then you have energy from the power grid and you're playing computer games. You're playing computer games directly dependent on energy in the power grid, and your generator also, your computer game playing is dependent on energy from generator. But they're kind of independent. But as soon as energy in the power grid drops or falls off, there is a shortage, the power generator kicks in and always compensates for the lack of energy. So you're always playing computer games. And so it's, exactly. No, but this is a violation of faithfulness assumption.
Yeah.
That means you are never able to establish that X and Y are actually independent from observations. The data will never tell you the true causal structure. So that's what faithfulness is. But we assume that people like Noah are very rare and unique, and situations as just described are also rare, so we don't consider them. We just go with causal and Markov, causal and faithfulness, Markov assumption and faithfulness assumption. You can interrupt me in your defense, no, but
I have no defense.
Yeah.
That's the best defense. He's letting you dig your own grave.
The right structure, causal structure for playing computer games and studying and all the stuff.
No, it is the same causal structure, right? But the faithfulness, because they seem we can fine tune, or they can we can fine tune the parameters such that they cancel each other perfectly. If they cancel each other perfectly, such that this parameter W2 and W1. So the effect of studying and the effect of this is a negative effect, right? Of game playing on the test, unless you're playing a game that is teaching you to pass this test or something like that, versus studying at the same time. So if they cancel each other perfectly, you will never be able to detect.
I learned more about history from playing Age of Empires than I ever learned in school.
But that's cheating, because it is a kind of educational game in a sense.
Not really.
Yeah. But anyways,
It's like saying StarCraft teaches you about space.
not about space.
It is
But
a little
it
bit
does
about
teach you
space.
about
There's There's stars in it. It's crafting.
Yeah,
but Minecraft is
Well, anyways. We are going to progress here. If we do that over and over again. Sorry, I was like, where's my friend? Okay, my notes. So consider this situation. And this is the we have three variables basically. So one other assumption that we usually employ, and that was originally employed, is causal sufficiency. In the simplest term, slightly incorrectly, causal sufficiency is that if those three variables interact, there are other variables, and you measure just those three variables. The other variables that are there, W1, W2, Wi, Wj, they don't matter, they don't point, like they don't interact with the variables that we're interested in. But the causal sufficiency assumption is a little weaker. It says that we have all the variables that we measure such that the variables that we don't measure only point into one of this variable of the measured variables at once. So if we have Wj, it only can point either to x or be pointed to by x, but pointed to, they can be whatever, we don't care. Any outgoing edges into that realm outside of this, they can do whatever they want. But the incoming edges from the unmeasured realm only to one of the variables, measured variables, either to y, either to z, either to z, y, etc. So we don't have unobserved common causes. That's the key. So if Wj points to x and to z, it's a common cause of x and z. So the causal sufficiency assumption is that the system is causally sufficient, that there are no unobserved causal common causes. The Direction of Time book by Hans Reichenbach is that there is not a situation like he described that associations are due to common causes. If there is a common cause, we assume we observe it. So then, okay, that we call this structure the collider, and well, I guess we'll discuss later. But what if it's the reverse, common cause, right? The z causes y, z causes x. Collider is when y and x cause z together. We say x and y are parents and z is a child. And now z is a parent and it's a common parent for x and y. So it turns out in this case that statistical tests of association, the better up to statistical errors, all the rules apply, the better the test you have, the better the data you have, can resolve those two cases. This case is very different from that, and see how it does. So we measure independence of x from y. Just what does it mean to measure independence of x from y? So we have a data set of samples 0, 1, and 2, or x, y, and z collected together. So what is this? Subject 1, subject 2. What is this? Time point. What like, or anything. So those are samples from the distribution. Assume time point will be tricky. We just assume for simplicity IID, so our statistical testing works correctly and everything.
Are you building a truth table?
No, I'm not building a truth table.
What is the table you build?
I'm building data. This is my data. Those are my samples. Samples I have for this point, that point, and random variable. I have a triplet. I have a value for x, value for y, and value for z, how they work together. If it's
binary or floating point,
yeah, or what, doesn't matter. It's up to you. Something that you can take this vector and that vector and measure independence of this vector from another one. If you can measure correlation and that's your independence measure, then that's okay, like use real value if you or whatever value you need for correlation. For binary, you can measure Hamming distance, there'll be that binary, some measure of association. If they're dissociated, they're independent, then fine. So in this case, in the first case, if you measure association of x and y, x and y are independent. They just x does something and y does something. They do their own thing. But if you condition on x, on z, sorry, if you condition on z here and measure those are two different tests. We say, okay, only measure umbrellas and okay, this is umbrella. Whether a person has umbrella, whether the pavement is wet. And well, this is umbrella and pavement actually are this situation. Okay, let's consider. So I'm considering there's three variables. X is whether people have umbrella or a person in this measurement, whether the pavement is wet and whether there was a rain. And I'm checking if I condition on the rain, will those umbrella and wet pavement become dependent or independent? So in this case, when you measure x and y, you see that umbrella and wet pavement are correlated. They're highly correlated. Association is high. The first test tells you association is high here, right? Well, it tells you they're associated no matter what.
So X or Y.
Umbrella.
tells you if they're correlated.
Hmm?
The first test being X or Y. The top equation.
I'm doing this test. Is x dependent on y?
So the answer to my question is yes.
Yes, they are dependent.
No, is that the equation you're using? What's my question? X or Y. That's an or symbol, correct?
No, there is no or symbol here.
What is that symbol?
Dependence or independence. This is independent. Oh, this is dependent. This is independent.
Okay,
So I'm just. It's a test of dependence
okay.
or independence actually. X is independent of y or not independent of y. So yeah, this is independence. So, but then now condition on rain, and if you condition on rain in this situation, they become independent. Because they become independent, you know, it is not this situation. If you were here, then, well, the moment umbrella and wet pavement are dependent, you know you're not here already. You make a test of x and y dependence, and if they are independent, then you're likely in case 1. If they are dependent, then you're likely in case 2. But you don't know yet, because there is this case, and there is that case. There are other 2 cases. There are 4 cases total here. So then you condition on Z. You say, okay, why don't I look at the days when there was no rain or there is rain, etc. And then you can find that once you condition, they become independent. So they become, what we say is they become conditionally independent. And from that you reconstruct, okay, well, this is my true structure. This is my true structure that is consistent with the results of my test. statistical test, and I can infer that the structure is causal up if my assumptions hold, Markov assumption and faithfulness assumption. So we can recover the V structure or Y structure on this side and versus common cause by using statistical tests based on statistical tests. But we cannot resolve the
Hey, can I ask a
case.
question?
Yeah, sure.
If you go back, I'm wondering on the notation at the top, shouldn't it be X given Z independent of Y given Z?
It's a statistical conditional independence test. It's not probability.
It's implied that both are conditioned on Z. That's what you mean.
They both are conditional on Z, right? It's
Okay,
it's
yeah, that's what I wanted to
precedence.
clarify.
Yeah,
Thanks.
it's a precedence kind of. It's just a standard notation. Sorry, yeah. But
Mhm.
yeah, you're right, Roger. Just the way to say it, and not necessarily delving in probability theory, Bayesianism, etc. You can still use statistical tests, frequencies, etc. But yeah, we cannot distinguish those two cases. So those two cases will be consistent with data, with the same data. You will do all the tests, conditional independence and dependence, and they will not be different. So I don't know if I need examples here. Anyways, let's skip from examples. The worst is that probably by statistical tests, you cannot distinguish, if you only have two variables, you cannot distinguish those two cases. You cannot tell whether X causes Y or Y causes X based on statistical tests, just as of association. Okay. So when people came up with this idea, I don't know who was first. The one I know is Spiritus, Glimmer, and Shyness in the book 1993 book, Philosophy Department, Carnegie Mellon. So philosophers are thinking about those problems that connect econometrics, machine learning, because it's applied statistics. Well, okay, let me say that just to make people mad. And a lot of algorithms came out of this fruitful idea. PC algorithm is uses the statistical tests to painfully, slowly recover the structure. It has causal sufficiency assumption. FCI, fast causal inference, does not have a causal sufficiency assumption. It allows unobserved common confounders, unobserved common causes. So if it thinks that association between variable A and B cannot be explained by statistical conditional independence tests, it says that it's like, okay, there is an external thing, like if there is an unexplained and a conditional on everything possible, I still have the dependence. And then extensions, etc., three-phase dependency analysis, RFCI, and as usual, I don't think I have more slides, but I can talk about, no. Then let me talk about the paper, from the paper. I'll still use my slides. So another alternative view to collect a bunch of independence tests and then try to put the results of them together, making sense of them, is the following. You establish or you define variables, whatever they are, again, X, Y, Z. You start with those variables. Let's have some time, system evolution. So you start with noise that is specific to X. It has probability distribution that is specific to X. And then there is noise that's specific to Y, and there is noise that's specific to Z. And then your causal structure, say is like that. It's nothing but f takes x and y, and so f is a deterministic function that takes two inputs, x and y. But noise is constantly working. So the way we display it is x has some value and has some noise. Y has some value and has some of its intrinsic noise. Z has some value and has some of its intrinsic noise. So let's have this, well, we don't want that structure. So let's have this structure, x, y, and z, for example. So what I'm trying to draw, there is always external variable here. And then what you actually have for y is a function of x and of z, but it's also implicitly a function of noise of z and noise of x. And the same for z, some other function, right? Let's call it fy just for now. This function is c, and it takes x and it takes nx, but it actually takes nz as well. So we need to have that will become important in a second. Interestingly, that x is nothing but its intrinsic noise now. Since there are no incoming edges into x, it's this whatever x produces we treat as a noisy variable. One of the key things to look here, okay, those f's are deterministic functions. And if we write, the question is, how does this z intrinsic noise of its own variable, how does it enter the picture? And the simplest and convenient way is the additive noise. So my z equals to whatever functional transformation, deterministic functional transformation of x and its internal noise, but x is just a noise, plus the noise of z. This is the model that they call additive noise model. But for now, when we have relationships that are functions, and we have noise attached to each and every random variable in this causal. So the noise, the point of the noise is it's independent. For each variable, it's its own noise. They're independent of each other, and the dependence is only from the variable. We have kind of a Markov, what is it? Markov random field kind of type of a model. We have a causal structure, and then we have another layer where the variables are totally independent. They only point down into each of the variables in the graph. But this approach is called structural equation models or structural causal models. It existed before that paper, used by many people. And one of the consequences of that representation is that if we represent our graph like that, we can score the entire graph. Like we can take the data and compute the likelihood, because first of all, we can parameterize somehow each of the relationship, and we can parameterize empty relationships as well. So like we set them to 0, and we can search for the value of parameters that gives us the best graph that in some sense fits to the data, and use one scoring usually.
Could you explain in a different language or simpler language what you mean by parameterize in this context?
So for example, yeah, easy. imagine that X takes values 1, 2, 3. It's what is it? Multinomial, trinomial, whatever, categorical random variable. It's either 1 or 2 or 3. And Z is either 1 or 2 or 3. And then to make Y probable, I need to consider all of the options, all of the values for pairs of X and Y. So like truth table like stuff. So they could be 1, 1, 1, 2, 1, 3, etc., etc., etc. And then there would be a probability assigned. That's my parameterization. What is the probability assigned to each of the combination that my Y becomes 1, 2, or 3? So for each of the combination, I need 3 probabilities. So this is my parameters. I don't know them. I need to set them. And I need to set them together with another parameter, which is whether this edge is on or off. So I need to look at all possible graphs with all possible parameterizations to find the optimal brute force. No one does that. Well, there is a way. But for Vista Suit 2000 something, I forgot the when they published it. There is a way to efficiently enumerate everything. But is the parameterization part clear? So 1, 1. You will have 3 parameters. One is probability, well, 2 parameters because of the degrees of freedom. One is probability that Y is 1, 2 is probability that Y is 2, and the third probability is 1 minus 1, minus probability of being 1 minus probability of being 2. So you need those 2 parameters. Structural equation model or structural causal model. Because you can score whatever entire model, you now can do a search in the space of the models and also find the causal structure. Greedy equivalence search is a representative of this approach. There are many others I don't remember off the top of my head. Sorry. Based on this approach, I forgot the word. Sorry. This thingy from Microsoft that we'll see soon see back. It was working based on this approach. The helping, non-helpful thing. What is the name of this feature in Microsoft Word?
Clippy.
Yeah, it worked on this approach. Turns out that those both approaches, the statistical test-based approach and the approach based on structural equation models as described on scoring-based approach, they are equivalent. They have the same limitations. They're absolutely equivalent approaches. They cannot distinguish a thing from that thing. But what the paper says is the powerful way of representing our models, separating the actual variable and the noise, and separating a relationship into deterministic function, allowed them to see and others to see interesting structures and approach the problem differently. No, we're not there. One is 2009 Hoyer et al. If you assume that your model, your noise is additive, then Hoyer et al. Remember that we cannot distinguish some structures, right? We have equivalence classes because of that. As soon as we have a structure like that, the colliders stick. Because we can distinguish colliders from non-colliders. We cannot distinguish this 1 from 2, but we can distinguish 3 from anything else. As soon as we have the 3 structure. So the equivalence classes there is all of the graphs that have the same skeleton when you drop the arrows, like the same skeleton, and the same colliders. And they are the same for both of the methods, but that's ambiguity. Given the same data, I'm not giving you one graph that fits it. I'm giving you multiple graphs that are perfectly in a in a maximally distinguished state from this with this data. Anyways, I'm doing what Brad predicted. Destroying myself by speaking.
Best argument is just quietly smile and nod.
Exactly. So Hoyer, Shimizu, and other interesting, nice people, by thinking in the functional based approach and by assigning square is the noise variable. I don't want to write any letters. By assigning this noise, realize that if you make an assumption that this noise are non-Gaussian, all of these noises are non-Gaussian and statistically independent, think ICA, then you can recover the causal structure uniquely. You can identify a causal structure uniquely, and the only assumption that's different from the previous models is additive noise models and non-Gaussian noises. All of them are non-Gaussian, well, plus up to one. Rogers will correct me if I'm going over. So looking at that, I have figures, but I cannot show them. The paper introduced this idea of causal and anti-causal or anti-causal learning. It says, okay, by looking at this functional approach for this noise, we can actually distinguish those two situations. And if we are predicting, I will show you. I will show bullet points for the same as usual. I will talk about it first. But if we are predicting y from x, right? We're predicting y from x. In this situation versus that situation, this is a causal learning because our y and x are aligned in causal relationship. We're predicting y, which is caused by x, from data on y and x. Versus this situation, we're predicting y, which is causing x, but we're predicting y from x. Which one is weirder, in your opinion?
Sorry, could you repeat the question?
So we're predicting that we are solving prediction problem. We're predicting y from x versus we're predicting x. No, we're predicting y from x here as well. But the causal mechanism is different. So the paper also introduces this independent causal mechanism. This causal mechanism is different in those two cases. Well, this is a MNIST case. We're predicting the digit 7, but the way the picture was produced is because the person had in mind 7, they wrote 7. The causal mechanism is reversed. The label defined what will be on the picture, not the picture defined the label. So the causal mechanism is reversed to what we're trying to predict. And yeah.
I think it's a bad example, but I get what you're saying.
So yeah, I agree. And this is a bad example, right? Because the label to digit is 1 to many. And so you're assuming.
No, when I write my digit, I write, even though you cannot read my handwriting, but I don't care, right? And that's how people manipulate, especially doctors.
But MNIST is not trained on a single person.
Yeah.
The label to digit is a 1 to many mapping.
But digit to label is 1-to-1 mapping.
Many to one.
The digit, okay, the label to digit
Which is fine.
No, not the 1-to-many. No. The person who wrote who made the picture, the person who made the picture was writing exactly the number they had in mind. They were not trying to write a different number.
First of all, I almost never write the same number the exact same way every time.
But the causal direction is still, you know what you're writing, right? It's not like you write something and then like, what number is that? Oh, okay, that's Homer Simpson
Yeah, but
making a
we're-
bet, but no, I don't.
Model, yeah, but
Yeah,
that's.
yeah, yeah.
The assumption there is you're about modeling the brain, but what I really want to ask about is, both can actually make sense but it depends on your association mechanism. If your association mechanism is symmetric, correlation or whatever, yeah. They should be the exact same.
There is no correlation. There is an observed common cause.
If it depends on your association, that's what you called it, right? Your association mechanism.
There is no association mechanism. There is also only causal mechanism.
So the first one makes sense because the time, if you consider time direction, the second one doesn't mean.
No, but you don't have time direction. You have the MNIST digits. They're already frozen in time. People already wrote that. And you're trying to reconstruct. Basically, you're solving an inverse problem. You're trying to figure out what did this person mean. Here, you're trying to solve the inverse problem. What did they mean when they wrote this number? They did write it in that way, but you're trying to reconstruct inverse problem. But they call it anticausal. That your prediction goes against. We're kind of running out of time, I'm afraid, and I didn't
So the
mention
person
all the
who-
key points here.
The person who wrote the letters in MNIST, they had like a Y prime in their mind, and they wrote the X, and then X.
No, they had the exact Y. They know that Y is a random variable. They had 7 in mind, and they wrote 7.
You might be better making an argument if you think of another example of a category causing the features of that category versus MNIST. Sounds like MNIST is fraud, and I agree with that.
It's just like reverse inference in cognitive psychology,
Or
right?
just any kind of almost unique thing, like instead of MNIST as labels, MNIST as their softmax values.
No, you're not getting it then. It's totally clear. You had in mind, the person who produced it had in mind one number.
A one-to-many mapping.
No.
The inverse of a one-to-many mapping cannot be a many-to-one mapping. Like, it doesn't work mathematically.
No, you're
Or
talking about
even
something
higher.
else. You're not getting what I'm saying. Yeah, you are. It's one to many.
The label to digit is one-to-many.
The label to picture,
Yes,
right?
label
There are
to.
tons of ways to write the same.
Yeah.
But the causal direction is one way, and it's very different. That's all.
Maybe an
The
argument.
mathematical argument of a
So
function.
you could have also written 7 as a Roman numeral 7, right? Yeah, and so that's what Sergey's kind of saying, I think, so.
Yeah, it
It's
doesn't
the
matter.
same, it's the same,
It's just this
Normal
narrow, and you're
number
trying to
7.
reconstruct.
but we have a different numeral for writing it.
Yeah. It could be anything, or you could written 7 kittens because you're.
So if we all
it's
wrote
a-
in Comic Sans?
Hmm?
If we all wrote. in
I mean,
Comic
honestly,
Sans?
yeah, Comic Sans, or if we went
Yeah,
back to.
Yeah, anyways, let me finish on this slide.
Cuneiform or something, yeah.
So the causal is predict effect from causes. That's the direction. And anti-causal is predict causes from effects. Maybe that's why they didn't call it inverse problem, because too many arguments here. But anti-causal is a new word. No one knows what it means. Let's use it. So predict causes from effects. That's all it is. So another set is causal learning is more robust to distribution shifts, specifically for generation. And that is the statement. Let me check one thing there if I have. No, okay, let's stop what it's quickly. Causal learning is more robust to distribution shifts, crucially for generation, because, and they have an example, but because of this assumption, independence of mechanism and input. So what they're saying, if you have X and Y, and for the sake of argument, let's say X causes Y, they are saying, and that's a strong assumption, but not so strong if you think about it. They're saying the conditional probability distribution. So imagine your joint has changed, or your PLX. As the data scientists, we're always looking at the joint. We don't have the conditional. This is the mechanism, the conditional mechanism. So they're saying if you change P of X, new data, you start doing new data. Your joint changes, but the mechanism changes, stays the same. The function that transfers, like that generates Y from X, stays the same. So This assumption of independence of mechanism is what they introduced in this paper and kind of urging us to think about those problems in this way. And then once you have this assumption, then you can see, as they show in the paper, but actually was shown in the paper before, that trying to predict y from x in this situation is different than trying to predict y from x in this situation. So we're still predicting y from x. I have a figure prepared, but it's not in my slides. Then additive noise models. Okay, it's also they kind of stick to additive noise model or post-additive noise model. Post-additive noise model is x equals some function of y plus noise, and only then, or well, x, and only then you apply some other nonlinearity. So post or post nonlinear or post additive, you apply nonlinearity. So it's either linear additive or not. And lingam is that algorithm that I was describing, unique identifiability. And the underlying causal structure is important for successful machine learning application, thanks to their assumption that our causal mechanism, the mechanism stays the same, the conditional distribution stays the same. We're truly out of time now, but let me show if let me see if I can get out one figure at least.
So in that situation, they were considering that node X is the input and the arrow is the mechanism, right? Is that kind of what's being suggested?
I'm not going to this. So and here, this, if you look at two variables x and y in the causal and anti-causal directions, then you can distinguish them that in the causal direction, the noise is independent of y, but in the anti-causal direction, excuse me, the noise is dependent on x, on the value of x. And then we know, okay, this is the one on the right is incorrect prediction. We can orient, not shown in this paper. This paper is more philosophical, but it's kind of a consequence of this frame of mind thinking about causal problems. But we can orient the edges now, even if you have two variables based on that. More variables, more tricky, but they introduce and go over like through a taxonomy or a zoo of different assumptions, which I didn't go through, but I did read everything. Under which the causal thinking helps and under which it doesn't. And they also consider when semi-supervised learning, adding unlabeled data helps and when it doesn't help. So that kind of goes back, or at least brings back home the self-supervised learning as well. But don't have a connection, just throwing it there. But for semi-supervised learning, sometimes throwing additional values of x may help, sometimes may not. I need to look it up again in which case. But for example, sometimes bringing additional values of just the labels can help you recover. It gives you additional information. So you don't have the measurements, you only have the distribution, new distribution of labels, how the labels are distributed in this context, and you can figure out the causal relations. So if you haven't read the paper and interested in that, I urge you to look at the paper. Well, we're out of time. Thanks everyone, and I'll see you next week. Is that you?
Yep.
Yeah,
Yes.
Brian will talk about something less controversial and more specific.
I think it's pretty controversial, actually, but
I don't know, I mean, it's cool.
Where do you?
can you bring your
post
tab